Okay, so as we move through statistics, you're going to read the terminology normal distribution quite often. And what normal distribution suggests is that your average is kind of in the middle. Okay? If something is normally distributed, your average is in the middle, and then it's like that normal bell curve surrounding it. So you picked up a second handout today, and this is a normal distribution bell curve, where your average is right in the middle. So right average there. And then this actually separates it into half standard deviations. All these numbers on the bottom are your standard deviation numbers. And it actually splits it up into half intervals. But we talked yesterday about being one standard deviation away from your average. And I'm going to put average / mean. So if I'm one standard deviation away, that could be up to here. I'm going to lightly shade that in. And one standard deviation below is right there. What was our percentage in theory that we were supposed to have between one, or within one standard deviation of our mean? 68. If you add up all of these percentages, 15 plus 19.1 plus another 19.1 plus another 15, you get 68.2%. 68% is a good enough rough estimate for us, but it's technically 68.2%. And what was it when you were 2 standard deviations away? 95, and this chart is going to show us if you go another standard deviation, so you go up to 2 above, and another standard deviation below, in total you'll be 2 below. If you add up all those numbers, 4.4 plus 9.2 plus 15 plus 19.1 and so on, all the way over here, you get 95.4% technically. And those are the two that you have to memorize, but I'm giving you this chart because in a lot of ways today, we're going to see, like, we're going to be asked questions about, what if you're 1.5 standard deviations away? Maybe not just one exact standard deviation away, but what if you're 1.5 standard deviations away? What is the chances of that happening? So we are going to keep coming back to this normal curve. So on our first exercise, we're asked for a population that is normally distributed. Find the percentage of the population that lies within one standard deviation. And we just got the exact number. We said 68.2%. And within 2 standard deviations, we just got to be 95.4%. You won't have to be that exact on your regions unless they give you something like this. If they don't give you something like this with the exact percentages, you're sticking with 68 and 95. Understand? Okay, 68 and 95. What percentage of the population is more than 3 standard deviations away from the mean? More than 3. So here's 3 standard deviations away. This percentage is more than 3 above. And down here, this percentage is more than 3 below. So when you add that up, what percentage is that? 0.2%, which is a tiny, tiny number. Much less than 1%. It's only 0.2%. The other 2 phrases in A and B were within 1 standard deviation or within 2 standard deviations. This is more than 3. So we had to go on the outside. This next one says between 1 and 2 standard deviations, specifically above the mean. So here's your average. Here's 1 standard deviation above, and here's 2 standard deviations above. So we're looking for between, right? They said between 1 and 2 above. So we need to add 9.2 with 4.4. So I'll show that work, but 9.2 plus 4.4 is 13.6%. Questions?
Wouldn't you say both of them, both 9.2 and 4.4?
No, because they specifically said above. That's a good question. If we did this one down here, now we're between one standard deviation and two standard deviations below. You see what I'm saying? Mm-hmm. If they wanted both, they would probably just leave it less specific, and they would say, what's the percentage chance that you're between 1 and 2 standard deviations away from the mean? So they haven't specified in that case above or below, so you would count both. But this particular one just specified being 1 to 2 standard deviations above. Okay? Exercise 2. Arlington High School has 424 juniors. On the math portion, the average was 540 with a standard deviation of 80. So here's the very first thing I want you to do. Sketch a graph of a normal curve. And right down the middle, you put the average, which was 540. And then we would list what's one standard deviation above 540. Since each standard deviation is 80, 620, and one standard deviation below, what'd you say? 460. What if I went a second standard deviation above? So I add another 80 to 620, 700, and a second standard deviation below, so I subtract another 80 from 460, 380. So this is my one standard deviation range away, and then I kind of opened it up to a second as well. So now the question is, what percent of the math scores fell between 500 and 660? What do you notice? Look at our curve. What do you notice about with the location of 500? What's that? It's in between. It's not one standard deviation. It's really actually only a half of a standard deviation, because halfway between 540 and 460 would be that 500 number. And the same is true with 660. Although 660 is halfway between one standard deviation and two standard deviations, so that's like 1.5. Okay, so that's 1.5 standard deviations above, and this is 1/2 of a standard deviation below. And this is asking for what percent fell between those, and we would go to our chart. 1/2 of a standard deviation below is here, and 1.5 standard deviations above is here. And so what's the percentage total that falls between there? And I'm going to add those all up. So 19.1, someone do that for me. 19.1 plus 19.1 plus 15 plus 9.2. 66.4%. Oh, 62.4%. So you sort of have to place these scores on your chart, okay? So I'm always going to encourage you to draw a picture like that. How many scores fell between 500 and 660? So we just got the percentage of the scores. This one's asking us, so how many people is that? That's 62.4% of the 424 kids that took the test. And so instead of giving it to us as a percentage, they want to know, okay, how many kids is that? So we would, how do you take a percentage of 424? What operation in math means of? Multiply. And I don't type in 62.4, what do I type in? .624, that's 62.4% as a decimal, of means multiplication, 424 kids, is going to tell me, now, what should we do to that number? Round, well, it's people, so to the nearest whole number, and they say that. Okay? 265 people. So 62.4% equates to 265 juniors. So far, so good? If Evan scored a 740, now, how many standard deviations away is 740 from 540? 2.5, says Anthony. And some of you are going to be naturally better than that, at that, than others. But we already decided that 700 was 2 standard deviations. We're not going up another 80 to 780. It only is asking us up to 740. So 740 is 2.5 standard deviations above. Right? Because 40 additional points out of 80 is an additional half of a standard deviation. Any questions on that? So what percent of the students did better than her? Look at your chart. Here's 2.5 standard deviations above. What percentage did better than her? 0.6%. So not even 1%. Okay? 0.6% did better than her. And it doesn't ask this, but I'm curious. What percentage of people did worse than her? Say it again. One more time. This is not 6%, this is 0.6%. If 0.6% did better than her, what percentage did worse? 99.4% did worse. And you guys might remember on standardized tests growing up, getting your percentile. If you took your PSATs, you get that as well. If you're in the 73rd percentile, that means that you did better than 73% of the kids. This Evan is in the 99.4 percentile, meaning it did better than 99.4% of the kids, which is phenomenal, right? She's at the top of the class. So we would say she's in the 99.4 percentile. And anytime you get that now, know what that means. Anytime you read what percentile you're in. When I go to the doctor and I find out that my child is in the 93rd percentile for his height, that means he's taller than 93% of other 2-year-old boys his age. I think it does it by gender. I don't know.
Yeah,
it does it?
It does.
Okay. So that's what that would mean. So they don't compare to all other 2-year-olds. They just compare to other 2-year-old boys. Yeah. Good stats questions. Every good statistician asks questions. Right, Cole?
It's so relevant. I mean, it's not to them yet, right?
Oh, yeah. You stats... Yeah, and when you read articles or you read about a study that proves something, you immediately wonder, like, who did they sample? Or how did they sample? And is this truly random? And you start to question the validity of a lot of things. Because stats, you can lie with stats very easily, and people who don't ask the questions and just take you for your word are going to be misled a lot of the time with stats. So approximately how many students did better than Evan? If 0.6% did better than her, then we need 0.6% of 424 students. And what decimal do I use for 0.6%? 0.006. Good, Scott. Anytime you're going from percent to a decimal, we move our decimal over 2 places to the left. So we do 0.006 times 424, which is not going to be a lot of kids. 2.544, so approximately 3 students did better than her. So she came in 4th place, right? She did pretty good. She did pretty well. Sorry. Jeez. All right. Exercise 3. The heights of 16-year-old teenage boys are normally distributed. Don't let that 16 fool you. That's not giving you anything about their height. That's telling you their age. So that's just a number that's in there to throw you. With a mean of 66. So when I draw my graph, 66 is going right in the middle. And a standard deviation of 3. So what's one standard deviation above, Molly? 69. And what's a second standard deviation above Jake Clancy?
85.
What's that?
85.
35?
85. Or
How big is each standard deviation? Jake, read that question again.
67. Or no.
Read the question again and answer my question. How large is each standard deviation? 3. So Molly went 3 above to get 1 standard deviation away, and I'm asking you what number would be 2 standard deviations away?
71. Or 2.
A second standard deviation away.
72.
72. So you go 3 units above and 3 units above, and if we wanted to go 3 standard deviations away, we would go up again to 75, and so on. And I would do the same thing below. If Jabari is 72 inches tall, which actually happens to fall right on our second standard deviation away, which of the following is closest to his percentile? So this means, percentile, remember, is the percentage of people that he's taller than. So I need to know what all of these percentages, right down to the very bitter end, add up to. He's taller than this many people. So if you go to your chart, we were 2 standard deviations away. I need to add up 4.4, all of these percentages, right down to the end. And I got 97.7. Okay? So he fell exactly on the second standard deviation mark, which means he was taller than all of these people. 97.7 percentile. I'm cheating, I'm writing percentile, which obviously is closest to 98. Good? Okay. Number 4. The amount of soda in a standard can is normally distributed with a mean of 12 ounces. Sketch your normal curve. Average is 12, always right down the middle in a normal distribution. The standard deviation is 0.6. So Jake Clancy, I'm going to let you go again. What would the numerical number be for 1 standard deviation above 12?
12.6.
12.6. How about 2?
13. Or no. 13.2.
Very good, 13.2. Okay, and 1 standard deviation below, if I go 0.6 below, I'm at 11.4. And a second standard deviation below that would be 10.8. Okay, so just wrap your head around it first. Don't overread. Just kind of give yourself a picture and figure out what's going on. 250 soda cans were pulled by a company to check volume. How many of those 250 would be expected to have less than 11.1 ounces? So where is 11.1 on our chart? Where's it? Right, it's halfway between these two. So it's not 1 standard deviation away, it's not quite 2, it's 1.5. So we're 1.5 standard deviations below. Now, our chart is always going to give us percentages. This is asking us for how many. We'll get there, but come up with the percentage first. Less than 11.1 ounces means you're less than 1.5 standard deviations below. So that's all of these numbers, agreed? Add those all up for your percentage. .7%. So this is 6.7%, but they're asking us for how many cans. So that's 6.7% of what number? 250. 250 cans. And then so we would just type in .067 times 250. And that's approximately 16.75 cans, which is impossible, right? You just go to your nearest whole number, which is 17. Any questions? Exercise 5. Biologists are studying the weights of crabs. They sample 16. You're asked to find the mean and the sample standard deviation, okay? Enter all that data into your calculator. Jacob, did you enter all that data into your calculator? I need you to enter that and then run your statistics. Okay, because there are 16 crabs, it could be easy to mistype something in. So when you type in your last crab, 15.1, make sure that's your 16th data point, so that you know you've got all the data. So if I stat calc, I don't have a frequency list. So if you have something in there from yesterday or from your homework, clear that out, because I should not have a frequency. Each of those crabs only got counted once, and then calculate. So my average is 12.6. The sample standard deviation, which one do I use for the sample standard deviation? The S. SX is 1.5. Okay, now that's the actual standard deviation of the sample numbers that we chose. Why does this sample indicate that the population would be well modeled using a normal distribution? Here's how. Look at your average, 12.6, and look at your median. If your average is right around the middle, and they both are right around 12.6, that's a good normal distribution. Okay? Meaning it's not skewed at all like we talked yesterday, where a certain high salary might pull up the average. There's no overwhelmingly large crab that's pulling up the average, and there's no overwhelmingly small crab that's pulling down the average. The average and the median are very close. So X bar is 12.6 and your median is 12.55. When these are very close, because these are very close, it's likely a normal distribution. Okay? Any questions on that? Versus that salary one that we looked at yesterday, where the median was $10,000 away from the average, probably not a normal distribution. Okay? So we flip to the back. Assuming your mean and standard deviation from Part A apply to a normally distributed population of crabs, what percent fall between 9.6 and 15.6? Well, we need our bell curve again. Our average was 15.6. Is that what I said? 12.6, shoot. 12.6. And our standard deviation was 1.5. So if I go 1.5 above 12.6, I get 14.1. If I go 1.5 more above that, I'm at 15.6, which is perfect because that's the upper limit of what we're looking for. And on the downside, if I go 1.5 lower than 12.6, I'm at 11.1. And 1.5 lower than that would be 2 standard deviations away, 9.6. Perfect. Those are my 2 limits. So they're exactly 2 standard deviations above and below. So looking at our chart, 2 above, 2 below. What did we say these all added up to on the chart? 95.4, was it? 90. That was Part A on the front. 95.4. So rather than adding that again, good. Okay, before we end here, actually cross this section out because I'm missing some diagrams. We did talk about these 2 histograms are not normal bell curves. These are not normal distributions. Both of these are skewed, okay? In this case, the averages are all pulled up, or the average is pulled up by all of these higher points, or maybe I would say that these pull the average down. But do you see how this kind of tails off to the left? Like this tails to the left? Okay? Professionally speaking, we would say that that is skewed left because it tails to the left. But the skew word is actually a vocab word. And the other graph tails off to the right. So it reaches its peak early and then it tails off longer to the right. That would be skewed right. And those are vocab words that are legit that you're going to read, and you got to know what that means. So think about your curve tailing off more to the left for skew left, and tailing. So those are not normal distributions. You would not be able to use your standard deviation percentages for something that's not normally distributed. Okay? You have a quiz coming up on Monday, so this is a normal homework assignment tonight.